All right, let's jump right in. Today, we're talking about Lewis structures, which are, the absolute bedrock for how we visualize molecules. But here's the cool part. We're also going to explore what happens when that simple drawing just doesn't tell the whole story.
So let's kick things off with a little puzzle, one that really bugged chemists for a while. Imagine you draw a molecule, and it looks perfect. It follows all the rules you've learned. But then you go into the lab, you look at the real thing, and it's totally different. What's going on there? How do we solve that mystery?
Okay, so to even understand the puzzle, we gotta get the basics down cold. And that means mastering the molecular blueprint itself. The Lewis structure. This is really the language we speak when we talk about molecules on paper.
And here's the roadmap we're gonna follow, our 5-step guide. It's super reliable. First, count up all your valence electrons. Second, draw the basic skeleton of the molecule. Third, stick the leftover electrons on as lone pairs. Fourth, make sure everyone's happy by forming multiple bonds to complete those octets. And finally, number 5, you assign formal charges to kind of double-check everything.
All right, let's get our hands dirty with a classic example, carbon dioxide, CO₃. So, step 1, count the electrons. Carbon is in group 14, so it's got 4 valence electrons. Oxygen's in group 16, so it has 6, and there are 2 of them. So 4 plus 6 plus 6, that gives us a grand total of 16 electrons in our budget.
Okay, step 2, the skeleton. The rule of thumb is the least electronegative atom goes in the middle. That's going to be carbon. So we'll put carbon in the center and stick an oxygen on either side, OCO. Each of those bonds uses up 2 electrons, so we've just spent 4. 16 minus 4 leaves us with 12 electrons to play with. We'll just sprinkle those around the outside atoms, the oxygens, as lone pairs.
But hold on a second. Take a look at that carbon in the middle. It's only got 4 electrons around it from those 2 bonds. It's not happy. It wants a full octet of 8. So how do we fix this? Well, we can borrow. We'll take a lone pair from the left oxygen and swing it down to make a double bond, and do the same thing with a pair from the right oxygen. And boom! Now carbon has 8 electrons, the oxygens still have 8, and everybody's stable. Perfect.
Okay, CO₂ was pretty straightforward, right? There was really only one good way to draw it. But what happens when you can draw a couple of different structures, and they all look kind of valid? We need a way to choose the best one, the one that's most likely to exist in reality. Chemists call this the dominant structure.
And our tool for making that choice is called formal charge. You can think of it like an accounting system for electrons. It's a way to check our work and see how the charge is distributed in our drawing. And here's the big rule: the best, most stable structure is the one where the formal charges are minimized. You want them as close to 0 as you can get.
So let's put this to the test with dinitrogen monoxide, N2O. Look at these 2 options. Structure A, well, the charges are a bit spread out, but it's not too bad. But now look at structure B. Yikes, this one's a complete disaster. Why? Well, for one, you've got 2 positive charges right next to each other. They're going to repel like crazy. And even worse, there's a positive charge on the oxygen. Oxygen is super electronegative. It hates being positive. So, yeah, we can pretty much throw structure B right in the trash. It's not a realistic option.
So this gives us our rules of the road for choosing the best structure. Rule number 1, get those formal charges as close to 0 as possible. Rule 2, if you have to have a negative charge, make sure you put it on the most electronegative atom, the one that's best at handling it. And rule 3, try to avoid putting the same charges right next to each other. Simple as that.
Okay, so we've got our rules, and they seem to work great. Everything's making sense, right up until the moment it doesn't. And now we get to the real heart of the puzzle we started with. Let's take a look at the nitrate ion, NO3-.
So we can go through our 5-step process, dot all the I's and cross all the T's, and we end up with this: a totally valid-looking Lewis structure for nitrate. The octets are full, the formal charges aren't too bad. But wait a minute, a question should be screaming at you right now. Why did I put the double bond on that oxygen at the top? Was there a reason?
And the answer is no. There was no reason at all. I could have just as easily put it on the oxygen on the right or the one on the bottom. All 3 of these drawings are, according to our rules, 100% equal. They're all equally valid. So which one is it? Which one is the real nitrate ion?
And this is where reality comes in and blows our minds. Because when scientists actually measure the bonds in a real nitrate ion, they find something incredible. All 3 bonds are identical. They're all exactly the same length, 124 picometers. and that length is somewhere in between a single bond and a double bond. So get this, none of our drawings were right, not a single one.
So clearly, our simple model of drawing one single structure has to evolve. The answer isn't that one of our drawings is the winner. The truth is actually a combination, a beautiful blend of all three of them. And this, my friends, is the amazing concept of resonance.
Now, this is super important. The molecule is not rapidly flipping back and forth between these three structures. That's not what's happening. It exists as a single entity, a sort of average or a hybrid of all three at the same time. The individual drawings we made, we call those resonance structures or contributors. They aren't real on their own, but they help us piece together what the real hybrid molecule looks like. So the big idea here is delocalization. That extra bond, that pi bond, isn't stuck between nitrogen and one oxygen. It's smeared out. It's shared equally across all three of them. That's what those dotted lines represent. And this spreading out of electrons, this delocalization, makes the molecule way, way more stable than any single one of our drawings would suggest.
Now, there are some strict rules for what counts as a valid resonance structure, and this is absolutely key, so listen up. The atoms themselves never move. You can't change the skeleton. All you're allowed to do is move electrons around. Specifically, you can push lone pairs into bonds and bonds back into lone pairs.
All right, time for a quick pop quiz. Let's think about ozone, O3. Based on what we just talked about, how many valid resonance structures can you draw for it? Go ahead, pause and think about it. Did you get two? One with the double bond on the left and one with the double bond on the right? If so, you nailed it. Okay, let's pull all these ideas together. We're going to wrap up by summarizing the key points you'll definitely want to have in your back pocket for any exam.
Think of this table as your ultimate cheat sheet for resonance. When you've got a few different resonance structures and you want to know which one is the most important, which one contributes the most to the real hybrid, just run down this list. Does it have more bonds? Are the formal charges minimized? Is the negative charge on the right atom? The structure that checks these boxes is going to be your major contributor.
So let's recap the journey we just took. We started with Lewis structures, our basic molecular blueprints. Then we added a layer of sophistication with formal charge to help us pick the best blueprint. And then, when even that wasn't enough, we unlocked this really profound idea of resonance, which shows us that the true picture is often a hybrid, with delocalized electrons that lead to incredible stability.
And that leaves us with one final thought to chew on. This extra stability you get from resonance isn't just a neat trick, it's a fundamental property of matter. So now that you see it, start thinking, what else could this explain? How might this hidden stability affect how a molecule reacts, what its shape is, or even how acidic it is? It's a huge concept. Thanks so much for watching.